So I was talking about the number systems. So basically there are 4 number systems that we use. The first is the decimal number system, which we are all aware of. Second is the binary number system, which uses only 2 digits, 0 and 1. Third is the octal number system, which uses 8 digits from 0 up to 7. And the hexadecimal number system, which uses 16 digits from 0 to 9 and then A to F. And to convert any decimal number into any of the other number systems, maybe hexadecimal or binary, we just divide that number by the base of the required number system. The base is basically the number of digits in that number system. For example, in binary it is 2. So for example, 45 is a decimal number and we need to convert it into binary. So we'll keep on dividing it by 2 and we'll note the remainder over here. For example, 45 divided by 2 gives 1 remainder and the quotient is 22, and we repeat the process, and all the remainders grouped together. This forms the equivalent binary representation of the decimal number. Similarly, for octal numbers, we'll divide the decimal number by 8 and we'll club all the remainders together to form the equivalent octal number. Similarly, for hexadecimal, for example, if 763 is divided by 16, we get 11 as remainder, that is B. And similarly, we get 47 as quotient, and we continue the process till we get 0, and we write all the remainders together. That is the equivalent hexadecimal number. Here are a few examples for conversion from decimal to binary, octal, and hexadecimal. You can go through as the slides will be provided. And for the reverse process, like if we want to convert a binary number or an octal or hexadecimal number to decimal, we'll use each and every position of the binary or octal or hexadecimal number has a place value which increases exponentially. Like the rightmost digit has the value base to the power 0. For example, for binary it would be 2 power 0, then 2 power 1, 2 power 2, and so on. For octal it will be 8 power 0, 8 power 1, and so on. And similarly for hexadecimal. So to convert any number in any number system to decimal, we will multiply the digit at that corresponding position with the place value of that number and add all the products to get the final number in decimal. For example, if we want to convert 101 from binary to decimal, so the first 1 has place value of 2 power 0, then 0 has place value of 2 power 1, and 1 has place value of 2 power 2. So if we multiply all these together and add, we get 5, which is the equivalent decimal number. Similarly, for octal numbers, we will multiply the corresponding digits with the place value of that digit, and we'll get the equivalent decimal number. Similarly, for hexadecimal. In hexadecimal, A corresponds to 10, B corresponds to 11, and so on, up to F, which corresponds to 15, and we'll multiply it with the corresponding place value to get the decimal number. And there is also yes?
recording में better दिखेगा.
Okay.
Zoom in a bit.
Okay, अब ठीक है. फुल स्क्रीन ही कर देता हूँ.
हाँ वही better.
So if there is also a shortcut method to convert any binary representation into its equivalent octal or hexadecimal. For example, here is a binary number. If we want to convert it into octal, we'll start from the rightmost and we'll club 3 bits together, because octal has base 8 and 8 numbers can be represented using 3 binary bits. So we'll club 3 bits together and we'll write the equivalent decimal of these groups. For example, decimal of 001 is 1, decimal of 110 is 6, decimal of 011 is 3, and so on. And then this 2361 will be the equivalent octal number of this binary representation. And for hexadecimal, since it uses 16 different digits and 16 combinations require 4 binary digits to be represented. So we'll club 4 binary bits together and we'll write the equivalent decimal number to form the hex. For example, here we have clubbed 4 bits together and the equivalent decimal of 0001 is 1, for 1111 is F or 15, and for 100 is 4. And so 4F1 is the equivalent hexadecimal representation of this binary number. And this was all about number systems. If you have any doubt, you can either write it in the chat box or you can raise your hand. And then we'll move to the logic gates. In digital electronics, logic gates is the most basic unit of digital electronics and combinational circuits or Boolean algebra, which takes input of 2 or more than 2 of Boolean variables and gives a single Boolean value as an output. By Boolean variables, I mean any variable which stores a Boolean value, and a Boolean value has only two possible values, either 0 or 1. You can interpret it as high or low, or true and false, and so on. So logic gates are basically the smallest unit of digital circuits, which takes input 2 or more Boolean values and it outputs one Boolean value. For example, there is one logic gate, AND gate, which takes input 2 or more Boolean values and it outputs a single value, which is the logical product of the two numbers. For example, here we can see the truth table. Truth table is nothing but a tabular representation of all the possible inputs and the corresponding outputs. So here you can see if both x and y are 0, the output is 0. If any of x and y is 0, then output would be 0, because AND gate is the logical product. And if output would be 1 only if both the inputs are 1. And similarly, we have the OR gate, which is the logical sum of the given inputs. So if any of the given inputs is 1 or high, then the output would be 1. Similarly, we have an inverter. An inverter basically inverts the Boolean value of the given input. If we give a 1, we'll get a 0 and vice versa. And buffer simply transmits the same value which is given as input, 0 for 0 and 1 for 1. Here is the pictorial representation of Boolean logic. For example, we'll consider A as whether a person has hair or not and B as beard. And if we do the logical product, then since B does not have an hair, so here it would be 0. So 0 into 1 would be 0 and 1 into 0 would be 1. So this represents logical AND, this represents logical OR, and this represents XOR, which we'll see now in the next slide. Similarly, we have a NAND gate. This is also a logic gate which returns the complemented form of the logical product of the given inputs. By logical product, I mean that all the given inputs are multiplied and the multiplied product is complemented. By complemented, I mean inverted. And similarly, we have a NOR gate which adds all the given logical inputs, logical sum, and then the logical sum is inverted or complemented. The inputs and the corresponding outputs can be seen here in the truth table. Similarly, we have a XOR gate, exclusive OR, which is whose equivalent output is represented as x into y complement plus x complement into y. So if we take the input x, logically multiply it with the complement of y. Similarly, we multiply y with the complement of x and we take the logical sum of the two. In a nutshell, we can say that XOR gate operates like this. If the given inputs are different, then we'll get a logic 1 as output, and if the given inputs are same, either 0 0 or 1 1, then the given output would be 0. And XNOR is just the complement of XOR gate. So here, if the given inputs are same, then the output would be 1, and if the inputs are different, then the output would be 0. It is just the complement of XOR gate. Then we'll have universal gates. Like there are two logic gates, NAND gate and NOR gate. The speciality of these two logic gates is that we can implement any other logic gate, be it AND, OR, NOT, XOR, XNOR, whatever logic gate we need, they can be implemented using some combination of NAND gates and NOR gates. Hence, they are known as universal logic gates because any other logic gate can be implemented using these two logic gates, NAND gate and NOR gate. NAND gate is the complement of the product of the inputs, and NOR gate is the complement of the sum of the inputs. Like here we can see that how we can realize the various logic gates using NAND gates and using NOR gates. For example, if we want to realize AND gate using NAND gates, so first we NAND the given inputs. So here at this point, at the output of the first NAND gate, the output would be x into y whole complement, and if we give that as inputs to the second NAND gate, so again that output would be complemented to x into y complements whole complement, that would be x into y equivalent. Similarly, here you can see that how OR gate is implemented, NOT gate is implemented, XOR gate, XNOR gate, any gate can be implemented using NAND gate. Similarly, we can implement any gate using NOR gates. For example, here x plus y whole complement would be the output of the first NOR gate, and again if we provide it as the input to the second NOR gate, then again that logical sum will be complemented and the equivalent expression would be x plus y or OR gate. So here all the equivalent circuits have been provided in which we can realize any other logic gates using NAND gates or NOR gates. So the next part of our consideration would be, for example, digital circuits are nothing but the implementation of some Boolean expressions. Like in maths, in algebra, we have mathematical expressions in terms of variables. Similarly, in digital circuits, we have Boolean expressions. These Boolean expressions may contain any number of variables and they may be lengthy. So our main task would be to simplify them, to make them shorter in length so that the implementation of those Boolean expressions would be easy using actual hardware or using logic gates. So basically there are two ways to minimize any given Boolean expression. We can either use Boolean algebra. Boolean algebra is governed by its own set of laws, which we'll see later in the next slides. And the second method is using K-map, or also called as Carnot map. This is a much simpler tabular method of minimizing Boolean expressions. So Boolean algebra, it is a set of rules to simplify any given Boolean expression. By Boolean expression, I mean any expression which contains variables as Boolean variables, and the operators are logical product or logical sum or etc. And the lengthy expression and the simplified expression would have no difference in their outputs. The equivalent output with the same. Basically, they are the same expressions, just simplified form of the longer one. So they will give the same output. So these are a set of rules of Boolean algebra. You can see the first rule is identity law, which states that 0 added to any Boolean variable and 1 multiplied to any Boolean variable will result in the same variable. The second law is null law, which states that 0 multiplied with any Boolean variable and 1 added to any Boolean variable would result in 0 and 1 respectively. Then we have the idempotent law, which states that any Boolean variable, when it is added or multiplied with itself, it will result in the same variable. It is fairly easy to conclude any Boolean variable can only have two possibilities, either 0 or 1. If a is 0, then 0 into 0 would be 0, which is a itself. And if a is 1, then 1 into 1 would be 1, which is a itself. Similarly, we can deduce it for a plus a. And then we have the inverse law, which is easy to conclude. If A is 1, then A complement would be 0, then 1 into 0 would be 0. Similarly, if A is 1, then A complement would be 0, so 1 plus 0 is 1. And then we have the commutative law. A into B is equal to B into A, and A plus B is equal to B into plus A, which states that the ordering of the logical addition or product of the variables does not matter. Similarly, we have the associative law, says the ordering does not matter. This is an important law, the distributive law, which will be later used in K-maps or converting the expressions into required form. Like A plus B into C is equal to A plus B into A plus C. This is an important law which should be kept in mind. And the absorption law, A into A plus B is equal to A. If we expand it, then we'll get A plus AB. And if we, like for the absorption law, A into A plus B, if we expand it, we will get A into A plus A into B. And by the idempotent law, we can say that A into A is A itself. So the equivalent expression would be A plus A into B. If we take A common, then we'll get A into 1 plus B. And by null law, we can say that 1 plus B is 1 itself. So A into 1, that would be A. So A into A plus B is A. And then we have the De Morgan's law. You can remember the De Morgan's law as break the line and change the sign. As here you can see that A into B whole complement. Here the operator or the sign was dot or logical product, and there was whole complement. So we will break the line on the top and we'll change the sign in the operator. So dot becomes plus and plus becomes dot, and the complement is broken. Similarly, here we'll break the line, change the sign. So plus becomes dot and the complement is broken. So A plus B whole complement is equivalent to A complement into B complement. These are the set of Boolean algebra, laws of Boolean algebra, which we will use to simplify Boolean expressions. These are fairly easy to prove. If you draw the truth table, you can easily see that all these laws are true and hold true. Here is an example of simplification of an expression using Boolean algebra. For example, this is a given Boolean expression, AB plus A times B plus C plus B times B plus C. If we expand the brackets, we get the A into B plus A into B plus A into C plus B into B plus B into C. We know that B into B is B itself from the above Boolean laws. So we'll write B in place of B into B. Similarly, we know that A into B plus A into B is A into B itself. So we'll write AB in place of this. And from I told you that this distributive law is important. We are using the same law here. You can see that A into AB is equal to A. We are using the same law here. B plus BC is equal to B. So this part we can write it as B. So if we take B common from B and AB, so we will get B multiplied by 1 plus A. And 1 plus A is 1 itself, so that equivalent expression would be B. And the simplified expression would be B plus AC. And you can see that this lengthy expression and this small expression B plus AC are equivalent, which means there is no difference in their outputs for the given all combinations of inputs. Only the expression has been simplified, and you can see that the circuit implementation also becomes a lot more simpler. It uses less number of logic gates, it will consume less power, and so on. The next topic is minterms and maxterms. This is nothing but a method of denoting Boolean expressions. A minterm consists, for example, we have any logical system which consists of 3 variables. It may consist of 4, 5, any number of variables. For example, we consider that it consists of 3 variables. So a minterm would be defined as any term which contains all the given variables in that digital system, either in its complement or in uncomplemented form. For example, if this system contains 3 variables A, B, and C, so here all the 3 variables are present, either in complement or uncomplement form. If a given variable is 0, we write it as complement, and if it is 1, we write it as it is. So this is a min term because it contains all the given variables, product of all the given variables in either complement or uncomplemented form. And then we have the max term, which consists of logical sum of all the given Boolean variables either in its complement or uncomplemented form. This follows the reverse notion of minterms. For minterms, we write complement if the given variable is 0, and we write the variable as it is if it is 1. But in max terms, it is the opposite. If the given value is 0, we write it as the variable itself, and if it is 1 or logic high, then we write it as complement. So these are minterms and max terms, which will be used later more prominently in K-maps for much easier method of simplification of Boolean expressions. So this is the method of designation of Boolean minterms and maxterms. For example, we can see that there are three variables in the system x, y, and z, and all the possible combinations from 0 to 7 have been written which x, y, and z can contribute. For example, if all the three variables are 0, then the corresponding minterm will contain the complement of all the three variables, and so the minterm would be x complement into y complement into z complement. Similarly, we can write all the minterms. If the given value is 0, then we write its complement form. If it is 1, we write the variable as it is. And since you can see that for the first row, the equivalent decimal value of 0, 0, 0 is 0. So it is designated as m subscript 0. Small m represents minterm, and subscript 0 represents 0, 0, 0, or all the three variables are complemented. Similarly, like for this example, 1, 0, 0. So this would be x into y complement into z complement. So the designation would be M4. Small m denotes minterm and 4 denotes 100, binary value. Binary equivalent of 4 is 100. So if I see anywhere small m subscript 4, I can easily deduce that since it is a small m, the given expression is a minterm, and since the subscript is 4, so the binary of 4 is 100. So the first variable will be in uncomplemented form, and the rest two will be complements. So it would be x into y complement into z complement. Similarly, if I am given the designation of any minterm in this form m0, m1, xo1, I can write the corresponding minterm. Same is the case with max terms, and I already told you that this holds in reverse. For example, if the given Boolean value is 0, then we write the uncomplemented form, and if it is 1, then we write the complemented form. So if x, y, and z all are 0, so we can see that the term is x plus y plus z, and the designation would be m0. Capital M denotes max term, and the subscript denotes the equivalent decimal value of the Boolean binary representation of the given input. For example, capital M subscript 3, corresponding Boolean binary value would be 0, 1, 1, and I can easily see that since it is a capital M, it is a max term, and since the subscript is 3, so its equivalent binary would be 0, 1, 1. The first value is 0, which represents that in max term it would be in uncomplemented form, and the next two values are 1, 1, which represents that they would be in complement form. So the max term would be x plus y complement plus z complement. In this way, given any designation, I can write the corresponding minterms and max terms. So next we consider another Boolean expressions. They are basically form of Boolean expressions. One is the sum of products form or SOP, and the second is the product of sums form or POS. We already studied minterms and max terms. Sum of product forms is nothing but logical sum of several minterms, and POS form is nothing but the logical product of various max terms. Like this is an example. Like if we have a given expression AB plus ABC, this is not a SOP form because here the first term does not contain C in either complement or uncomplemented form. Similarly, we can convert, for example, this is a given expression, but it is not in SOP form, but we can convert it into SOP form. Like for example, I can say that the given expression is AB plus ABC. So this term does not contain C in either complement or uncomplemented form. So we will multiply it with C plus C complement and we'll write ABC. We know that C plus C complement is 1 itself. It will not alter the value of AB. So we multiply it with C plus C complement to convert it into SOP form. So this would give ABC plus AB into C complement plus ABC. And since ABC, ABC are same, we can further simplify it like this. So you can see that this expression contains all the three variables in either as a complement or uncomplemented form. So this is a valid SOP expression. So in this way, I can convert a given Boolean expression into SOP form. Similarly, this is the method of implementation of an SOP expression. An SOP expression would just be some minterms would be there, or some means that some Boolean variables would be multiplied, and then those multiplied terms would be added. So here it would form a series of AND gates which will multiply the respective terms. They may be either in complement or uncomplemented form, and then those would be added. We can also use a NAND gate to do the same. NAND gate would multiply the variables and then complement them. We again complement the given inputs and give it to the OR gate to add them. So the equivalent output would be the same. Similarly, we have the POS form. For example, here is a given expression A plus B into A plus B plus C. Here you can see that the second term contains all the three variables A, B and C, but the first term does not contain C. So to convert it into POS form, we can convert it like this, like A plus B into A plus B plus C. In the first bracket, we can write A plus B plus C into C complement. We know by Boolean laws that C into C complement would be 0 itself, so it would not alter the value of the first bracket. And by another Boolean law, we can expand this bracket as A plus B plus C into A plus B plus C complement. We know that there was a Boolean law. It stated that A plus BC is equal to A plus B into A plus C. We are using the same Boolean law over here. We are considering this as the first term and this as the second term, and we are expanding. So here we can see that both the terms are in POS form because they are the logical sum of the given Boolean values in either complement or uncomplemented form, and all the terms contain all the variables in all complement or uncomplement form. So this was all about SOP and POS. This is the method of implementation of POS. Since first the Boolean values are added, so we use OR gates, and then all the sums are multiplied, so the second step would be an AND gate. I've already discussed this, that any standard SOP or POS expression is that which in which all the terms of the corresponding SOP or POS expression contain all the given Boolean variables of that system. For example, you can see that in these examples, all the terms contain all the three variables A, B, and C. So this is an example of standard SOP and POS form. Here is an example. For example, this is a given Boolean expression. Here the sigma term denotes min terms, SOP form, because in SOP form we add the sum of product form. So the sigma denotes that the given Boolean expression is in SOP form. If the given Boolean expression were in POS form, then we would have used a pi symbol over here. But since it is a sigma, it denotes that it is an SOP form. And second, we can see that the numbers given in the brackets denote that for the equivalent input, for example 2 4 5 6 7, so we convert 2 into binary, that would be 0 1 0, right? So similarly for 4 it would be 1 0 0, for 5 1 0 1 1 1 0 and 1 1 1. So the given values 2 4 5 6 7 denote that the output of this Boolean expression would be 1 only when the decimal equivalent of the input sequence is either 2 or 4 or 5 or 6 or 7. So you can see the truth table has been constructed. Here are the A, B, C are the input Boolean values and F is the output, and the output is 1 only when the input sequence is 2 in equivalent decimal, 2, 4, 5, 6 or 7. Then only the input sequence is 1. So we can easily write the equivalent SOP expression. For example, the output is 1 for M2 or 0 1 0. So the SOP expression for this would be A complement into B into C complement. Similarly for this, it would be A into B complement into C complement. For 5, it would be A into B complement into C, and so on. So in this way, we can write all the min terms together and get the equivalent SOP expression, and then we can minimize the given SOP expression using Boolean laws. Like, for example, there is a Boolean expression given in POS form, and this comes out to be the equivalent POS expression. So you can easily simplify it using Boolean laws and get the equivalent output. And using Boolean laws and Boolean algebra to simplify Boolean expressions may seem easy, and it is easy for systems consisting of 2 variables, 3 variables, and in some cases up to 4 variables. But if the number of variables increases beyond that, for example 5 variable systems or 10 variable system, or the length of the Boolean expression is too long, so it would not be very much convenient to simplify the given Boolean expression using standard Boolean algebra laws. So for that, we use K-maps, which is a much easier tabular method of simplifying Boolean expression. From here, Sandeepan would take over. Sandeepan?
Yeah, just a minute.
Over
I'll
to
present
you.
my screen. Okay. So how much did you guys understand what is SOP, what is POS? Is it clear? Anyone, you can just unmute and say.
Yes,
Is my screen visible? Okay. So as Sachin asked, what about the part where we have more than three variables? So then obviously we resort to a technique called K-maps. Now we can have even more, but we'll restrict our workshop only to 4 variables. For 5 variables, I'll give you further material which you can pursue on your own. Okay, so what is a K-map? It's a graphical technique used to simplify logic equation. Yeah, whatever the POS SOP term you're getting, the big term you're getting, you want to simplify that, obviously, right? And So it's a technique which is invented by Carnot. So and there you make a grid box and where you write down numbers from 0 to whatever number of variables you have. If there are 3 variables, you write 8, you make 8 squares. If there are 4, you make 16 squares. So I'll be coming to that later on. I will just show you what are K-maps and how you will be making them, and you will get a minimized circuit. Okay, so I'll just glance through the slide. So these are some rules that you use for making the K-maps. Construct a label for this. I'll rather show you the K-map for first. Yeah. So this is a K-map for two variables, right? For two variables, if you have this, and for three variables, you can see a K-map looks like this. For two variables, you can have 4 possibilities. So you have 4 squares. For 3 variables, you have 8 possibilities. You have 8 squares. And similarly, for 4 variables, you have 16. Right? Like, uh, yeah, like you can see here, you have a 4 variable K-map. So now I'll come back. Now the thing that we use here is we make something called groups. Assume you have a SOP, right? Sum of products. So in that, what will you be using? Zeros or ones? Obviously, you'll be using ones, right? So you write down wherever the function is one, you make the truth table, right? And for whichever combination of ABC your function is coming out to be one, for those values you write them down inside these boxes. And the number you're representing can be read like CAV. So 000 001. So the first box is 0 in decimal. This is 1. This is 3 because you see it's 0 1 1, right? So that will become in decimal it will become 3. And then you have 2. So it goes 0 1 3 2 and then 4 5 7 6. So if you are wondering why 3 and 2 are swapped here and not 2 and 3, that is because that is the technique that is used to simplify the equation, right? You have if you notice in every column and in every row, only one term changes. From 0 0 you go to 0 1, and then from 0 1 you go to 1 1. Instead of if you went from 0 1 to 1 0, you would have two swaps, right? 0 changes to 1, 1 changes to 0. Instead, here you have 0 changing to 1 itself, right? So this is something called gray code, and this is used to simplify the circuit. So the boxes represent 0 1 3 2 4 5 6 7, as I told you, 4 5 7 6, right? Okay, so these are swapped. And just keep a note for 4 variables. You will have 0 1 3 2, right? 4 1 0 0 5 6 7, right? For 0 1 1 0, 4 5 7 6. But from here you have 1 1 0 0. That is, anyone tell me what is 1 1 0 0 in decimal quickly? Just unmute and say 1 1 0 0.
10,
Come
yeah.
on.
12. 12.
Yeah, who said 12? You're right. So 8 plus 4 becomes 12, right? So 12, 13, 15, 14. And in the final row, now you have 8. 8, 9, 11, 10. Cool. Anyways, it was given here itself, so fine. Coming back. So for wherever the function f is 1, right, you you write 1 in those boxes, right? And now what you have to do is you have to group them up. In what ways can you group them up? You can have uh, a group of 8, a group of 4, a group of 2, or someone who's left alone, single, like most of you, I guess. And so that's the ways you can group these ones, right? And our objective is to group up these ones, starting from first you look at the map, right? And you notice and you check whether you can form an octet anywhere. An octet is 8 ones you can form in a group, horizontal and vertical, but not diagonally. Okay, as you can see, this is it's an invalid group, whereas these are two valid groups, right? 1 1 can be a part of many groups. Okay, and I'll come to the part where you cannot have one a part of a group. But if you notice here, this is a valid grouping, right? Because I have 1 1 in horizontal, 1 1 vertical, and this one is a part of two groups, but this is still valid. But you cannot have a diagonal 1 1 or anything of that sort. Okay, whatever will be, there has to be horizontal and vertical. So if you notice in the map below, the first one, here you can form a group of 4, right? You can combine 0 1 3 and 2. That is one octet, and another, sorry, that is one quad. Another quad you have is 3 2 7 6, right? this box here. So one is this box and another is this box. And if you notice, these two ones are overlapping for both boxes, but that's fine. Okay, and this is valid and this one is invalid on the right. Why? Because first our objective is to look at octets, if there are any possible octet. Octet is a group of 8. Then you come to quad, and if then you come to pairs. So if this one can be a part of a quad or an octet, so there's no use in breaking up, right? The aim is to unify things. So we instead of making 3 or 4 pairs, we make one quad, right? So this quad can be broken down into 2 pairs or 3 pairs, but that is wrong. We will be having just a single quad. So the group should be as large as possible. That is exactly what I said. First to look at the largest groups and to come down the hierarchy. And this should be horizontal or vertical, but not diagonal. Always remember that. Now, another bonus point, groups may wrap around the table. Okay. So think of it like a game. These guys can also come up and form a group with these guys. They can wrap around. The first cell here can wrap around with the fourth cell. And similarly, the fifth cell can wrap around with the last cell. Okay. And the same applies for vertically also. As you can see, yeah, so it applies vertically as well, but it again doesn't apply diagonally. Okay, it only applies horizontally and vertically. So if you notice here, the grouping that you have is a quad, right? This one here, one second. Cell number standing for 0, for 4, and for 2, and yeah, that is 6, right? So these 4 form together a quad by wrapping around. And similarly, you can have another quad here with 0, 2, then 4, and yeah. So it's the same thing, right? So you can either have it here horizontally, vertically, but you can only have one of them because they're exactly the same, right? Now coming to the important point, when is a group redundant? Now we can introduce the term, the concept of redundancy. A group is redundant when, like as in this case, you can form 2 groups, right? One horizontally and vertically. That's wrong. You will be forming only one. Whenever all the members of a group are a part of 2 groups, or are a part of more than one group, then that group is found redundant. Okay, always remember this. Like if you notice in the first one here, it's correct, right? Because this first one, the one for the leftmost one and the topmost one, these two haven't been covered, right? These two are a part of only one. They aren't a part of more than one group, so they're correct. So that is not a redundant group. So I'll come back there. Yeah, even in this example, if you notice the first box, uh, the last row that you see, that the green row and the red, right? They are 2 quads, as you can notice, right? There are a group of 4 ones. So why is it not redundant? There are 2 because cell number 4 and 5, right, of the green row, those those are a part of only a single group, and the same applies for cell number 3 and cell number 2, right? So as long as there are members of a group which are not a part of more than one group, that group cannot be termed redundant. So and now what do you do if a group is redundant? If a group is redundant, you don't have to do anything. Simply just mark it that it isn't a group anymore. Just keep it make all the members of the group a part of one group. Just remove whatever thing you thought, whatever other grouping you saw, just remove it. Okay, just drop that group. And what happens? So you have octets, you have quads, you have pairs. And what happens if you have a single guy? If you have a single guy, you don't have to do anything about it. Just leave it alone. Just as you can see in this case, this one right here, the green one in the last table, rightmost table in this row, in this slide, that one is a miserable single one. So you can't do anything with it and just leave it alone. Okay. No simplification is possible for that particular term. And now, how do you write the minimized expression from this K-map? Okay. So I'll take an example. Okay. So I'll start with this itself. Say you're given a function summation of 0, 4. So I assume that your understanding of SOP is correct. So as whatever I just taught, So summation of 0, 4 means you put in 0 and 4 there, right? 0 and 4, as you can see, you put 1 in for both of them, correct? And this is the easiest K-map that you can ever have. You just have a single pair, right? Now, if you notice, this bar, A has been written here and BC has been written there. So the rows represent A and the column combinations represent B and C. Okay, so you'll be reading it the same way. Like A. Now, once you have a pair, just see while traversing through all the members of a group, right? Just see the variables. Just see the variable that is not changing. Okay, so the one that changes, you don't write it in the term. That's it. So if you notice in this case, A is changing from 0 to 1. So do not write it. What you will be writing is BC, BC bar, right? Because 00 stands for 1 second. Okay, so we'll be writing 00. 00 stands for B bar C bar, obviously, right? 00. So 00 stands for B. If you are not realizing, then 00 stands for B bar C bar. 01 stands for B bar C. 11 stands for BC, and 10 stands for. Can someone tell me what 10 stands for in terms of B and C? Anyone?
BC bar.
BC bar, right? So what we'll be writing here is B bar C bar, because that is the one that is not changing, right? For this row, don't write A because it is changing from 0 to 1. The second example you take, here you have summation of 4 and 5. So mark in 4 and 5, correct? And now if you see, then you see that C is changing from 0 to 1, but A and B remain constant, right? A and B bar. So A remains constant here, and B is 0 in both. So both of them get retained, and it becomes AB bar, correct? Third example, you have 0, 1, 4, 5. Then again, you for the first time, now you see a quad, right? Now the good thing about a quad is obviously there are changes in a row as well as a column. So two guys will get eliminated here, and you are left with only one. And what is that? B bar. If you notice, B bar is 0. I mean, if you notice, then B is 0 for all these 4 elements, right? For 0, 1, 4, and 5, B is 0 for all of them. Other variables change. Here, with the exception being that it's a very straightforward case where you see that only A is constant here, and that is A bar, stands for 0, right? So similarly for this pair, and the first time you see a wraparound pair here, and a wraparound pair again, you notice that here in example number 6, right? You see that 1 second, yeah, you see that C does not change, right? And C is 0, so you write C bar, and obviously A also does not change, so you write AC bar, correct? Another wraparound pair and the wraparound quad at the end. So I'll leave that for you to figure out yourself. Now that is it for 3 variable K-maps. Now coming to a 4 variable K-map. Okay. Now obviously there are 4 variables here, so you can have 16 combinations, and the table also looks more symmetric and better than the previous one. Again, the rules are same. You fill in all the tables. You fill in the table as per your function, and so here are some examples you can see. The concept is exactly the same. It's just that the groupings get a bit more complicated here. So like in the first case, you can see you have, I mean, you can see the groupings, right? Just look at the groupings and you see that is the most optimal way you can do it. You could also have grouped these ones out here but it will come out to be the same if you notice. So if you can see here, you can group these ones here which are a part of already 2 groups. But why haven't you grouped them? There are more groupings possible if you notice carefully, right? I can for example, I can club cell number 0, 1, 3, 2. I can club in cell number 4, 5, right? And then 12 and 13, right? Can I do that? Someone tell me. Cell 4, 5, 12, and 13. That is the first 2 cells of the second row and the third row. Hello, someone just say if you can. Okay, so I'll just say, yeah, of course you can. You could have done it, but if you notice, if you club these guys out, then the ones in the bottom row, they get left out, right? You can then again you have then I mean the point is that in whatever way you do it, you will still have three quads. Okay, you can't minimize it anymore. You notice in this case there are three quads, and when whichever way you club it, you can club in the first four ones, you can club in the second four ones together, you can club in multiple ones, but at the same but if you club in if you make in all the groups possible, we'll notice that one of them gets redundant, will have to get redundant. All the ones of one group will have to be covered in more than one group, so you don't do that. Okay, and then the same another complicated case you can see here. So as you can understand that it's not quite an easy concept. So what I recommend is you go to some you go to some YouTube videos. You can also go to some links on Geeks for Geeks to understand this K-maps. All you need is some practice, okay? And you don't need anything more than that. This bit of practice will help you to identify what groups you can make out, and the simple and the most simple version of the function you can get. Okay. Also, there are a lot of K-map solvers online, so you can for testing yourself out, you can just randomly select. You can randomly make the map, okay, and then you can minimize it yourself and just see whether the result is right. So I highly recommend doing that to a lot of you. That's the easiest and fastest way to learn. Just draw random tables and try minimizing the circuit yourself. Okay. Uh, one more concept I would like to introduce you now is don't cares. So you shouldn't be caring about your x's, right? And we represent don't cares in our K-map by x. Okay. You can in a K-map you can have either one, you can have a zero, or you can have an x. So what are these x's? Basically, we tell here that we do not care about that variable. It may be either 0 or 1. We don't absolutely care about it. Okay. Uh, and what is the benefit of doing that? Like in the cases where like it's like an if else statement, right? You can it's like a case statement. It can either be 1, it can either be 0. Now if it is a 1, then maybe you can group it up. Maybe we can form a larger groups, right? And simplify expression mode, right? And if it is a 0, then we don't. So the point is that it doesn't matter whether we take it or not. If it helps us in forming a larger group, then we take it. Otherwise, we don't care about it. It's a 0. It doesn't exist. Okay. So I'll give you an example again here. In this expression, you can see, yeah, and it's denoted by D. Okay. Uh, so if you see 0, 3, 5, and 12, they have been represented by an X in the map, right? 0, 3, 5, and 12. There are 4 X's in the map, and you can see they correspond to that. Now, if you notice that uh, cell number 1, yeah, the first, the blue box, basically the blue box. Now that like it is possible to make the blue box because we have that X, right? We have the X in 5. So including that X helps us in making a quad here, right? So therefore we make that quad. And the same applies for the red box and the green box. So whenever, and if you notice the first cross for 0, that we have left out. Why? Because we can afford to leave out our X, right? We can afford to leave it out. So we can afford to leave it out, but if it helps us in forming any bigger group, then we take it. Okay. So again, you can also put in don't guess in that K-map solvers you can have online, and you can just draw random maps and try solving them yourself and then checking the result. It's highly recommended for you to do that. And now enough of this boring theory. Okay, time to see some gates in action. I'll show you some gates live. Just give me a minute. And if anyone has any doubts, you can ask me right now because I'll be stopping my slides now. And I'll be showing you some circuits. If anyone has any doubts, you can ask. These K-maps are really useful in minimizing your circuits, as you can see, and this the event is basically about how much you can minimize your hardware requirements. So if you can make a circuit using 1 gate instead of 3 and 4, then obviously that helps in minimizing the cost of the circuit. Okay, so that's why this is a very important concept which all of you must know. And I guess the first PS will be based on this itself. So this is a very important concept you should know.
Yeah, hello,
And just
Bhaiya.
give me a minute. I'll give. Yeah, say.
One doubt. Yeah, we have to minimize the hardware using K-max, but there are different possibility to club all the ones or zeros. So
Yeah,
how we know that it is the minimum possible, minimum required hardware? No.
yeah. So as I was saying, this thing, uh, if you follow the rules, you'll always end up with the most minimized circuit, right? You'll always end up with that. You'll always end up with that, or the most, or the and an equivalent of that. So that's right. Uh, and the way you can do that is again, as I said, you have to practice a lot. It takes a lot of practice to know, to identify groups, which to identify the largest groups and and the groups which is not redundant, right? As a beginner, often you will identify a lot of redundant groups. You will mark out all the octets, you will mark out all the quads, and then you will notice that some of them are membered of more than one group. So then you just scratch them out, one of them, and you just leave them in one group. And so that's how you proceed. Okay, try forming as many groups as you can, and notice the ones which are redundant and remove them. Okay, and so practice on online K-map solvers, or go to some articles or YouTube videos, and it's quite an easy concept. It won't take you much time. Just take some practice.
Okay, Bhaiya. Thank you, Bhaiya.
Okay. Yeah. And one more thing I forgot to say. For 4 variables I showed you, and for 5 variables, there's uh, there's another way you can have two variables of 4 maps, two 4 variable can have stacked one after the other, and you can have that simplification also, which isn't quite hard. So if you want, you can just have a go to that on the net when you want. But for 6 variables and more, we normally don't use k-maps, okay, because it gets quite complicated. You cannot have 3 stacked k-maps and start solving them in your mind. So for that, we have separate techniques, but we are going to limit our scope up till 4 variables for the moment, or even up to 5 we can consider. But 6 variables is out of the scope for this workshop and this event as well. We have other methods like you can search it up online what methods are there other than this. But this k-maps are the most efficient way for solving functions for less than equal to 5 variables. Okay, so just a minute. Yeah. So this is Proteus. I think you are introduced to this software in Exavata. And don't worry, I'll provide you the links of all these softwares and all uh, later on. We'll officially introduce you to the software some in the third workshop or fourth one. So up till then, I'll be just showing you some glimpses and some practical things on to help you better understand what I'm teaching, right? So can someone tell me what the first gate is on the left? Anyone? Just move it quickly and
And
say.
wait, Bhaiya.
Yeah. So okay. Who said it? Hello. Can you say your
Yes,
name?
Bhaiya. Vishal, Vishal.
Vishal. Right. Okay. So tell me what are all the gates here? First you have the AND. Next, the second one. Uh, row. Go down the
Jor,
column. Okay. And XOR. Okay. Number 3.
Or
or,
So so this one is OR. Correct. Then this one is NOT. Obviously, you can see it on the
NAND,
screen.
NAND,
This one is right. You're correct. NAND. This one.
inverter,
Yeah, that is inverter. Correct. And the last one.
it is NOR.
no.
Yeah, fine. Correct. So I'll just show you what happens when I run the simulation. So basically here I have the gates. I have both the inputs connected to a logic state, right? And the output will be coming in these question marks when I play on the click button. So as you can see, for the AND gate for 0 0 you have 0, for the OR gate you have 0 here again, for the NOT gate you have 1 here, and similarly it follows. And when you change the logic states, then for AND you have to have both ones for 1. If even a single of them becomes 1, you have a 1 here. NOT gate inverts. XOR inverts here as well. Again, comes back to 0. 0. Then similarly for the NAND gate, if I make both one term 0 and here again it becomes 0. So you can play around with that. So that is one circuit I showed you. Now I'll show an example on K-maps, right? Okay, 1 second. So now there's a quick, we have a quick exercise for you. Maybe you can solve it. Wait, 1 second. And it's exactly what I've taught you in the last few slides. So maybe you can have a go at it if I've understood. If any one of you knew K-maps from before, then it should be easy for you. So how many of you are trying? Is anyone trying right now?
Yes, we are.
Okay, take your time. So I'm giving 5 minutes for this. Okay. Just try and tell me what you're getting.
Yes, yeah.
Yeah, so what did you get?
Where we need to simplify or we just need to write whatever we are getting from the K map?
uh, Whatever getting from the K-map, that itself is the most simplified version, right? You cannot simplify further. If you can simplify, that means you made
So
an error. Yeah,
I'm not sure because I haven't like revised it, but I'm getting
that's
something like AD plus A complement B CD complement plus AB complement CD. No, it's not right.
okay. Yeah, not exactly.
Yeah.
Anyways, and Vishal,
Yeah, yeah. I got A complement, B complement, plus I think D complement, B complement, plus AD, plus A complement, A complement, C complement, I think.
okay, doesn't look correct, but I'll just show the solution as well. I'll just walk you through the solution once. So wait, I was sharing. So yeah, so this is the solution as you can see. So what did you have? You have 1, 3, 4, 6, 8, 9, right? You fill in all the. So for the other guys, you can have a look at the solution. Just understand. So if again you fill in all the numbers given inside the summation of m as ones, right? As you can see here, you put in ones for 1, 3, for 1, 3, 4, 6, 13, 15, 8, 9, and 1 and 11. Okay, and for the don't cares, which is represented by the D summation D, you put in 0, 2, and 14, right? Yeah. So if you notice, 0, 2, and 14 have been denoted by an X in the map, and then you start simplifying it. So again, with practice, we'll observe that this is the best way to do it. Once you start from octets, quads, and pairs. So octet, you can see you don't have any octet, right? Now you can have now there are multiple quads that I can see immediately, and all of them have been grouped here, as you can notice, with the green box, yellow box, brown box, and there are in fact even more. Uh, some members which are already part of another group, all of them. Like the first two itself, I can see is a quad, but all of them are a part of some other group already, right? So I do not take that. And all of the pairs, all of the terms here have been covered by quads, except for the x on 14. And since that is an x, we simply don't care. So you get AD plus B bar D plus B bar C bar plus A bar D bar. This is the final expression you're getting. And yeah, if you list write down the terms after this, and this is what we'll be getting. So yeah, and
Yeah.
just one. Yeah,
Is it necessary to make quad like in that? Will you show that K map again? Yeah, sir. So,
make
Bhaiya,
what?
there
Okay.
you like made the quad of 0, 4, and 2, 6. And no, sorry, sir. 0,
Yeah,
1, and 8, 9. And then you
0,
again
1, 8,
made
9.
a.
Okay.
So you again make a quad for 0, 4, and 2, 6. So, sir, can like you can only make a duplet now of 8 and 9. You can just make a duplet and 0 and 1 also.
Yeah, that's the point. Now we do not want to make duplets, right? If
Yeah.
anything can be grouped inside a, we start from wherever first you see if you can make a if you can make an octet. If you can't, then you go for a quad. If you can't, then you go for a duplet. So here I can see that I can group 8901 inside a quad, right? So I'll go for a quad.
Mm, yeah.
So always
Okay,
remember
so
that you
if we
start from
can
the basic.
make a quad, we have to make the quad.
Yeah, yeah, exactly. You do
Okay,
not make
thank you.
a duplet instead of a quad. Okay. So always start in that hierarchy: octet, quad, and duplet. Cool. Uh, and yeah, so I wanted to just show you this circuit also. So just a minute. Yeah. So um, what was the term we got? the first anyways, I can't show both together, so just show you what it is. In here it is if you can see the 4 logic states on the left, right, the ones which have a 0 on them. So they are A, B, C, D, where A is the bottommost one. Okay, so the MSB is A. I've taken the MSB to be the most significant bit to be A. I hope you know what the most significant bit and least significant bit are, right? Anyone can tell me what the most significant bit is in general?
Left one होगा.
Yeah. So the left one, the one having the most amount of weight, right? That is the most significant bit. And the rightmost bit you have in the binary number, that is the least significant bit, which contributes the least to the number. So here the MSB, the one on the bottom, I've taken to be A. So this one I've taken to be A, right? And it goes A, B, C, D. It goes like that. Cool. So and the same circuit, whatever was the result of that came up, which you got, which is AD plus B bar D plus B bar C bar plus A bar D bar. If you notice that I have 4 AND gates for all of them, NOT gates for inverting each of them, and then 2 OR gates sum it up, and another OR gate to sum up the result of that. Right. So if I play it, then for 0 the answer is 1. Right. So basically, if I can abstract this entire part inside a single circuit. So if my input to the circuit is 4 zeros, ABCD is 0, then my output is 1. And if you remember, the question was 1 was there in the K map. So we had 1, 3, 4, 6, 8, 9, and some more terms. So 1 you have, okay, 0 was a don't care. In the K map there, 0 was a don't care. So as you can see, we don't care whether the output is 1 or 0. We are not using this output anywhere when it is 0 actually. Okay, so that's the concept behind don't cares. We don't care for that input, what the output is. So it doesn't matter to me whether the output is 0 or 1. But what I cared about is 1, 3, 4, 6, 8, 9, 11, 13, 15. So there for 1 I have 1, for 3 also I have 1, right? For 4, 6, 8, 9 I should also have 1. So if I'm putting 4, it's still 1, 6, then come back to 8, 9, 11, and after that you had 13, 15. So 15 and 13 as well. It's all 1. Now 2 isn't a part of this. So if I put in 2 here, if you notice, then 1 second. 2 was a part, right? 2 was a don't care again. 2 was a don't care, so I don't care whether it's 0 or 1. So 5 is definitely not a part of any of the things. Neither a don't care nor a part of the thing. So 5 is supposed to give me 0. So if I put in 5, so I'll be getting a 0. Okay, so that entire function which we had right there has been simplified to just these few gates. Just simplifying, just reducing the cost of hardware by a huge extent. So that is the power that K-maps give you, right? So for 5, then even 7, 12, I should be getting a 0. 7 also I'm getting a 0, and same goes for 12. So I'm getting zeros out here. So you have obtained, you have made the circuit that converts the corresponding input to this output. Okay, I guess so. That is enough. I guess you have understood the concept why you should be going to K-maps, right? How crucial it is, and it's just because it's the very basics of digital electronics, right? You anyone, I mean, if you say I know digital electronics, then the first thing to start off with is K-map, Boolean algebra and K-map. So this is the right most fundamental basics. So you should have a thorough knowledge of it. And one last final thing I would like to give you is a homework question. Okay, so listen to it carefully. It's not written on anywhere. Just listen to it and try it out yourself. Yeah, imagine I am asking you to make a circuit, okay, which adds 3 to a number. Just simply adds 3 to a number. Okay, I just want you to do that. So if for 0 I'll be getting 3, for 1 I'll be getting 4, for 2 I'll be getting 5, and so on. Up till say take it till 7. 7 gives me 10. Okay, so just try out that, and don't use an adder. When try to make the function yourself. So we make columns A, B, C, D. You have 3 variable sets A, B, C, and you have corresponding outputs X, Y, Z. You have 3 inputs, you have 3 outputs, right? So your function, the circuit should convert these 3 inputs, and it should give me those 3 outputs. For 0, I should be getting 3, 1, 4, 0.25 and like that similar correspondingly. So just try it out yourself at home before the next workshop, because next workshop will be introducing adders and more of that combinational circuits, so which are more interesting than what we taught today. So do join the next workshop as well. So with that, I would
Wait,
like to
can
end
you
this
repeat
workshop.
the question? Can you repeat the question?
Okay. The question is, make a circuit or make a function. Basically, just give me f. Okay, f equal to, just give me the expression. For 0 input, I should be getting 3. For 1, I should be getting 4. For 2, I should be getting 5, and so on. For 7, I should be getting up to 10. Okay, so like that.
Okay.
A function which adds basically 3 to a
And can
number.
you please share some resources from where we can practice K-map and these logic gates?
Kmap, I told you, right? You can just search online Kmap solver, and you can just put in the zeros and ones you want in the table, and then you can try solving it yourself, and the result also will be getting in that simulator only online. That's the best way to do it. Other than that, you can go to some YouTube videos. I'll share those links of that. Okay, but the best way I would personally say is for you to practice yourself, and the online tools are the best thing for that. I'll be sharing a bit of YouTube videos as well, and yeah, that is fine. Yes. Ultimately, it's up to how much you
Okay, bye.
practice.
Okay, thank you.
So, anyone has any doubts or anything to ask? Anything you did not understand? I know for some of you this might not be clear, the terms I introduced and we taught today, but go back to the recordings and go back to the workshop content later on, and you will definitely understand it. Okay, so with that we end the workshop.